I'm Anil Kumar. Welcome to my series on trigonometric functions. In this video, we'll discuss graph of secant functions. Major topics which will be considered will be how do we graph transformed secant functions and how do we write equation from the given graph. We'll begin with the relation between cosine and the secant function. We'll graph secant function. We'll understand the concept of sketching the graph of reciprocal functions. There is an idea of reciprocals which we'll discuss. It's kind of a new strategy which I find very amazing. We're going to use this strategy to sketch very easily graphs of transformed secant functions. And thereafter, we'll find equation from the given graph. Some practice examples will be given to you to practice all the learnings. Well, here are a few graphs which illustrates how do we sketch from a cosine function a secant function, which is the reciprocal of the same. We'll take them one by one in the following examples. Let us begin with checking the concept of reciprocal functions. For the following functions, f of x is reciprocal of g of x, which is written as f of x equals to 1 over g of x, where denominator g of x is not equal to 0. That is how normally we'll define a reciprocal function. Well, remember that this f inverse is not reciprocal, right? So if you have f something like to the power of minus 1, it is basically inverse of a function. It is not a reciprocal, okay? Now with that said, let's take up an example here, question number 1. You need to answer this question. If f of x is approaching 0 from the left hand side, read as f of x is approaching 0 from negative side, then reciprocal of f of x is approaching what? 4 choices are given to you. You can pause the video, answer, and then look into my suggestions. Here is question number 2. If f of x is equal to minus 2 over 3, then the value of g of x is what? Remember, g of x is reciprocal of f of x, correct? Let's answer the very first one. So when we say f of x is approaching 0 from the negative side, think like this. Let us say that at this particular point, somewhere here, the function is approaching 0 from the negative side. Do you see? Approaching from the negative side. Correct. So in that case, what is going to be the value of g of x? That is what we are interested in finding, right? So if f of x is approaching 0 from the negative side, then the reciprocal of f of x, which means 1 over f of x, is approaching what? So when you're approaching 0, negative, reciprocal is always with the same sign, correct? And therefore, what do we expect here? We expect it will be approaching a very high negative value, right? So sometimes we will denote it like this. You get an idea, right? So that is what it is approaching to. So option D is the right option. It is approaching negative infinity. Okay, question number 2. F of x is minus 2 over 3. The value of g of x, which is reciprocal of f of x, will be what? The sign will be maintained as negative, but it will flip 3 over 2. So negative 3 over 2 is what the reciprocal of this value is. Perfect. So with that in mind, let us now understand the relation between cosine and secant function. As you know, secant is 1 over cosine function, correct? So here are the characteristics of cosine functions along with the secant function. So let's try to compare them one by one. Period of both is 360. If you're working in radians, you can write this as 2 pi, right? Period for both will be 2 pi. Now, range of the cosine function. So here we have actually sketched the cosine function. Let me highlight one wave. So that is the cosine function we are talking about, right? Uh, let's say this. So in fact, the wave actually starts from the portion here, right? So that is the zero, right? This is the wave we're talking about, okay? So as you can see here, 360 degrees is one period. It starts with maximum, goes to 0, minimum, 0, maximum. Range of f of x is between +1 and -1, correct? That is what the range is. As far as secant is concerned, it is greater than +1 or it is less than -1. So the absolute value of secant x is always greater than equal to 1, whereas the absolute value of cosecant x is less than or equal to 1. And both have even symmetry. All right, so both have even symmetry. Now let's look into concavity. As you can see here, this part of the graph is concave down, right? So concave down between -90 to +90. However, the secant graph in the corresponding period is concave up, right? So that is concave up. In the other half, what we see is that the concavity is concave up for cosine, but concave down for the secant. Now here are a few key points on a cycle to remember. 0, 1 is the maximum value for the cos function. So that is at 0, the value 1 is the maximum. Then at 90, we get a 0. Then minimum at 180, minimum value of -1. At 270, it is back to 0. And at 360, it is again the maximum value. As far as the secant function is concerned, the values 0, 1, and these are invariant values, right? So you see these are common points, correct? So we say that the local maximum and the local minimum, they are invariant, they're common to both cosine and the secant functions. On the other hand, we see that the zeros, which are these values, the zeros on the cosine function will be the vertical asymptotes on the secant functions, right? So these vertical asymptotes are shown here. These are the vertical asymptotes. So these vertical asymptotes on the secant functions correspond to the zeros of the cosine function. That is what the reciprocal is, correct? So that is how the two graphs are related. Now these characteristics really help us to sketch accurate graph for secant functions from cosine functions, right? So let's take example and further explore. So we'll graph the function of the form a times secant x. That means it is vertically stretched by a factor of a. Example, sketch transform secant function y equals to 2 secant x. Now we'll adopt two different methods to do this sketching of the graph. In the first method, as you know, uh, secant is the reciprocal of cosine function. So we'll sketch the reciprocal of cosine basically, and then we'll stretch the graph vertically by a factor of 2 to get 2 times secant x. So the steps involved will be, if you look at the equation, which is y equals to 2 secant x, it is 1 over cos x times 2. So basically, we can sketch the graph of cosine function, which is done here. So that's the graph of cosine function which we have sketched. And then we can actually do the reciprocal of this. So step 1 is to sketch cosecant x, and step 2 is to sketch the reciprocal. That is to get 1 over secant x, correct? So that is what we have done. And step 3 is to incorporate vertical stretch, right? So by a factor of 2. So these are the 3 steps involved to sketch the secant function from the cosecant function. As mentioned here, first we are going to graph y equals to cos x. Now remember, when you graph y equals to cos x, you identify the zeros, correct? So those are the zeros. Now at these zeros, we expect a vertical asymptote. So these zeros corresponds to the vertical asymptote on the cosecant function as I'm highlighting now, right? Okay. Then we also learned that these are the invariant points, the local maximum and minimum. While in cos, these are the absolute maximum minimum also. So since they are invariant points, those are common to both cosine and the secant function. We also learn that the concavity changes at these points, since that local maximum becomes the minimum value for the secant, right? After all, secant is 1 over cos x. So if you divide by a lower value, you get a high value. If you divide by high value, you get a lower value, correct? And so the concavity flips, and therefore, for the secant function, we actually get a graph as shown here, which is on the other side, right? The concavity flips. You get the idea. So that way we get the graph of y equals to secant x just by flipping it. So let's get back to this. Zeros for cosine functions are at 90 times odd multiples of 90, right? 2n plus 1, odd multiples of 90. And the extreme values are at the multiples of 180. And as you've seen, cos is less than or equal to 1, in between plus and minus 1. It is concave up in one portion, then concave down. That is how the concavity changes. Above the axis, it is concave down, and below the axis, it is concave up. Perfect. So when you have to sketch the secant function, then the zeros get converted to the vertical asymptotes as I was discussing. The invariant points are common, which are at the turning points, and the secant values are greater than 1 or less than minus 1. So we can write absolute value of secant is greater than equal to 1. And we can flip the concavity to get the graph of secant x. Perfect. So we got the graph of secant x. Now it is question of incorporating the vertical stretch by a factor of 2. So that means all the y values get multiplied. So 1 becomes 2, and likewise all the values get multiplied by 2, and so vertical stretch by a factor of 2 gives us the required function 2 secant x as shown here, right? So the values for the range of secant function now is greater than or equal to 2 or less than equal to minus 2. Okay? So that is how we could sketch it. So that becomes a way of sketching. Now here we'll observe one very critical thing. In this whole gap, which we see right there, right? The question here is to think about is, can y equals to 2x fit in the void space on the final graph? That is what is important to understand. So can we draw a cosine function here? So I think we can. We can actually just join these points, right? And if you join these points, you do get a cosine function. So that really means that instead of sketching cos x, we could have started with 2 times cos x. You get the idea. So the step number 1 could be sketch 2 times cos x, and then at each 0, we have the vertical asymptotes, perfect, and flip on the concavity with invariant points, right? So we could actually sketch cos 2x, 2 times cos x straight away and get the graph of y equals to 2 secant x. You get the idea. Let's explore that idea, right? That is what we call alternate method, method number 2. So we'll again do the same question, which is to sketch the graph of y equals to 2 secant x. But this time our method will change. We'll actually sketch the graph of 2 cosecant x and then flip it over. Okay, so here is what we have. We have a graph of cosine x. So these are the zeros of the cos x function. These are the invariant points. So we have sketched the cosine function here, which is 2 cos x, right? Vertical stretch has already been taken care of. Now, if I draw the vertical asymptotes for the zeros, since secant is a reciprocal function, zeros will be converted to vertical asymptotes, right? And we flip over from the invariant points, then what do we get? We get the secant function which we got last time. Exactly same function. You get the idea. So that is very important to understand. The result is absolutely same. Perfect. So, but this is much easier way of sketching. So that is what we call as idea of reciprocals. Remember, 2 cos x is not reciprocal of secant 2 secant x, correct? Remember that part, right? So you should remember that uh, secant x and cosecant x are reciprocal. However, 2 cosecant x is not reciprocal of 2 secant x. However, for the sketching of graph, it works. You get the idea. So this is what we call as our idea of reciprocals, right? So important thing here we learned is about the idea of reciprocals. And this is what we are going to explore and graph all the functions. So let's look into this idea of reciprocals once again. So the idea of reciprocals summarized below will be utilized to sketch the graph of transformed reciprocal functions from primary sinusoidal functions. So we are going to use this strategy for secant x as well as cosecant x, okay? So that is what we are talking about, primary sinusoidal functions. So important things which we learned is, one, zeros transform to vertical asymptotes, right? So for vertical asymptotes, I'll be writing VA most of the places. Turning points are the local extreme values. They could be local maximum or local minimum. Now these extreme values are the only common points in both the graphs, correct? Concavity reverses at these common points. Range overlaps at the turning points only. So there is only one point which is common to the function and it's reciprocal when we talk about the secant and cosecant or even sine and cosecant. Secant and cosine and sine and cosecant. Okay, now period of reciprocal sinusoidal function is exactly same as that of the sinusoidal function, correct? Then cosine and secant have even symmetry, sine and cosecant have odd symmetry. So the symmetry is also maintained between the function and its reciprocal when we are talking about the sinusoidal functions. Let's take examples to illustrate this. So we'll graph the function of the form a secant k x minus p plus q. That is a transformed function in general. Let's take an example here. So the example is 3 secant half x plus 1. So we'll try to graph this using our concept of idea of reciprocals, correct? Let's repeat and review the concept. So we know that 3 secant half x plus 1 could be written as 3 over cos half x. So that is secant half x is reciprocal plus 1. And of course, the denominator is not equal to 0. Wherever this denominator is 0, that becomes a vertical asymptote, correct? So basically it means that the function is not defined for cos of half x equals to 0. So these zeros, wherever it is not defined, results into the vertical asymptotes for the secant function, right? That is one thing. Second is, when we look into the maximum value of 3 over cos half x plus 1, it is 4, correct? And 4 becomes the local minimum value for the secant function, correct? These are invariant points, right? So maximum and minimum values basically are invariant points. These are the only common points, right? Or you can say where the range overlaps. Perfect. So those are those maximum minimum points, correct? So from here we analyze that if we sketch the graph of 3 cos half x plus 1 using the idea of reciprocals, then we can directly sketch the graph of 3 secant half x plus 1, correct? That's the whole thing. Okay. Now here is a very important note for you to understand, and that is uh, 3 cos half of x plus 1 is not reciprocal of 3 sine half x plus 1. Remember that, correct? Okay, second, the zeros of cos of half x match with the vertical asymptotes of the whole function, whole secant function, right? And then invariant points of 3 cos half x plus 1 are the same with 3 secant half x plus 1. Now, these are very critical things to understand when we talk about the idea of reciprocals, correct? Let's sketch this function to really understand what we are trying to say. So the function which we are going to sketch is 3 secant half x plus 1. So the idea here is, first, we are going to sketch the cosine function, which is cos of half x. Now you can see this graph is the graph for cos of half x. So once you sketch this graph, then we have to mark the zeros. So sketch, mark the zeros. Which are the zeros? Well, these are the zeros for this particular graph, correct? So mark these zeros. These zeros will be the vertical asymptotes for the secant function, correct? So at these zeros, we are going to draw the vertical asymptotes. As you can see here, so that is the vertical asymptote which is through the zero of our cosine function. You get the idea, right? So first phase, all those zeros are marked and they result into the vertical asymptotes for the secant function. So that is step number 1. Okay. So we mark the zeros and then we draw the vertical asymptotes at these zeros. So that becomes the first thing. Then second step, we actually stretch the cosine function and translate it 1 unit up. So that is what is being done in the second graph of the cosine function, which is stretched, and also it is translated 1 unit up, correct? So that is the stretch factor which we have incorporated by a factor of 3, and then it is translated up. The axis has now moved up by 1 unit, as you can see. Do you see that? So earlier the axis was right there. It has now moved 1 unit. So what we have here is the equivalent reciprocal function, which is for us 3 cos of half x plus 1, correct? We got this function now. We already have formed the vertical asymptotes as very clearly shown here, right? And now, what do we need to do? We need to sketch the secant function by marking the common points, which are the turning points on the cosine function, and then flipping over the concavity, correct? Once you do that, you get your secant function. Is that clear to you? That is how we are going to sketch the secant function which was given to us. So I hope you understand the concept straightforward. You are an expert in sketching cosine and sine functions, so their reciprocals now should not be a problem, right? So I hope you got this concept. Now let's take one more example. Now here in this example, what are we going to do? Well, here we will find the equation from the graph. So now the idea is find the equation from the graph, and the equation will be of a general form. So let's try to do it. We expect the equation to be a secant kx plus q. That means no phase shift in this example, right? So we'll take another example with phase shift. Let's look into it. When we say no phase shift, basically we expecting, well, that's the axis, correct? We're talking about. Okay, so at 0, we do have a point which is local minimum for secant function. So that means clearly there is no phase shift, right? And so we just continue. I'm just marking these points since that is going to help me to get the equation of the graph. Can you tell me why did I mark these points? Well, these points here give me local maximum and minimum value. So as you can see here, the local maximum is 4 and the local minimum is minus 2. So I'm reading this value. This is minus 2 and that one is 4. So I mark these values and I'll fit in the cosine function in between. So I'm kind of doing the reverse. I'm trying to find the cosine function, and from there, using the idea of reciprocals, I'm going to write down the secant function. See the beauty of this. Once I get the maximum minimum point, I can find the axis, which is average value, right? So this is the average value, add them, divide by 2. Axis is at 1. So at 1, I got the axis for this particular figure. So this is the axis, right? So I'm just sketching it here. Then there's a neat sketch down below, which you can see there. Okay, now amplitude. Amplitude is difference of maximum minimum divided by 2. Amplitude is 3. You can see 1, 2, and 3 units up, correct? And 3 units down, 1, 2, and 3. Perfect. So we get the amplitude. We know the phase shift is 0. Now let's see the period. Now period is the distance between the two local maximums or two local minimums. So in this particular case, we get a period of 180 degrees. So that's the period of 180 degrees. Value of k is 360 by the period. So we get the value of k as 2. Since the phase shift is 0, the cosine function, which you could sketch here, right? You could sketch here the cosine function, correct? Which I've done here. Now, look at this graph, green. Green graph is the cosine function which we are talking about, correct? And we know this is the axis shown in orange, and those are your invariant points, correct? The graph equation shown here is 3 cos 2x plus 1. All these values we got are the ones which we just calculated, right? So these are the values. When you substitute, you get the equation for the cosine function. Now, using the idea of reciprocal, just replace cos with secant and you get your result. So we get our final function as 3 secant 2x plus 1. Perfect. That is how we can very easily get the equation of the secant function from the given graph. Got it, right? Let's take another example. This time I'm doing with radian measurements, right? So we had been focusing on degree most of the time. In this example, we'll find the equation from the given graph using radians because along the x-axis we have 4 pi written, 2 pi written means radians, correct? So the question here is determine the equation of the function in the form of a secant kx plus q. Again, the idea here is to somehow sketch a cosine function in between, right? So here we have to sketch cosine function, correct? Once you sketch a cosine function, you get this equation and then you get the secant equation also. For that, we'll look into the local maximum and the local minimum. The value of local maximum here is 3. Local minimum is -1. Then find the axis, which is the average value. Add them, divide by 2. You get a value of 1. The amplitude is difference of these two values. You get amplitude as 2. Right? So we got the value of amplitude. We got the value of Q from these two. Perfect. Now let's look into the time period. Well, these two local minimums are 4 pi apart. That means the period is 4 pi. The value of k will be 2 pi divided by 4 pi is half. So we get the value of k as half. Now we have all these values. We can write down our function, this time first in cosine, because that is the cosine wave which we just got. You got it, right? Whose equation is y equals to 2 cos half x plus 1. And how do we get the secant? Just change cos to secant and you have your result. You get it. That is how we are going to do it. Perfect. Last example is in which we are going to have a phase shift. And now let us also focus on how do we get the phase shift from the function itself. So this time we'll get an equation which will involve the phase shift. Okay, so the equation will be x minus p plus q. Okay, so the graph of the secant function is given to you. From here, we'll find the cosine graph. So again, we'll start with marking the maximum minimum points and then see, well, what are their values? So in this particular case, the maximum value is 5 and the minimum value is 1. So those 5 and 1 are written. Find the axis, add them, divide by 2, you get a value of 3. Axis really means that the q value is 3, correct? So we know q is 3. Then find the difference, get the amplitude A, which is 2. And then find the time period. So between the two minimums, you can find what is the difference. In this particular case, it is pi. So the period is pi. The value of k is 2 pi by pi, which is 2. So we get k equals to 2. Now the question is, how do we find the phase shift? Okay, let us first join these points and get our cosine functions. So first thing first, the axis is at 3. 1, 2, and 3. So that is the axis. Let's sketch this axis. Now the cosine function, which is, we have the maximum here, minimum here, right? So, and the minimum here, so the cosine function graph, we can just combine these things, join them, and draw the function. I'll do a better job than this. Okay, let's redo the axis. Correct. And now let me sketch the cos function here, right? So that is how the cos function could be. Okay, which we have drawn here in green. So look at this cosine function, which is perfectly as shown earlier. Perfect. So within this cos function, we have to now figure out what is the phase shift. How can you do it? Well, look at the point where you have the maximum. So this maximum is pi by 4 on the left, and therefore the phase shift is pi by 4 left. You get the idea, right? So it should be minus pi by 4. So when you incorporate this value, we get p equals to minus pi by 4, correct? So in the formula, we can substitute the values just calculated. We get 2 cosecant 2 x plus pi by 4 plus 3 as our equation. Replacing the cos value with the secant, we get the curve given to us, which is a secant graph equation. You get the idea, correct? That is how we could do it. Perfect. So you see how easily we have actually got the equation from the given graph for the secant function. Perfect. So I hope that really gives you a good insight. The key idea which we explored here is the idea of reciprocals. In spite of the fact that the whole equation was not the reciprocal, we utilized the concept to sketch the graph and also to find the equation of the graph. I hope you understand and appreciate it. In case you want to learn from me, you can always send me an email on the given address. We're also updating our website. You can always check it for the latest videos. Thanks for your time and all the best.